Welcome to AI Frontiers, where cutting-edge research meets real-world impact. Today we're diving into a startling discovery. Artificial intelligence systems worldwide are making millions of decisions every second, with hidden moral biases we're only just beginning to understand. Join us as we explore 15 groundbreaking papers from September 12, 2025, revealing how AI systems coordinate like orchestras, detect their own failures, and embed specific ethical viewpoints that could reshape human-AI collaboration forever. Picture this reality. Right now, AI systems are making millions of decisions every second across the globe. They're diagnosing diseases in hospitals, executing trades on financial markets, moderating content on social platforms, and curating what appears in your social media feeds. But here's the startling revelation from recent research. Many of these systems operate with hidden moral biases that we're only beginning to comprehend. Studies reveal that 6 major language models consistently show the same ethical preferences, raising profound questions about how these systems influence human decision-making. The boundary between human and artificial intelligence decision-making is becoming increasingly blurred, with implications that extend far beyond simple automation. Today's journey takes us through 15 remarkable discoveries that are actively shaping our technological future. We'll encounter AI agents capable of detecting their own failures using sophisticated information theory principles. Imagine systems that recognize when they're confused and proactively seek assistance. We'll explore multi-agent systems that coordinate with the precision of synchronized orchestras, each AI component understanding its role while contributing to a larger emergent intelligence. Perhaps most concerning, we'll uncover how advanced language models embed specific moral viewpoints into their responses, potentially influencing human ethical reasoning at unprecedented scales. We'll also examine medical AI systems that can explain their life-or-death reasoning processes step by step, and discover virtual economies where AI agents engage in complex trading and negotiation behaviors. The field of computer science and artificial intelligence resembles a vast, interconnected metropolis, where different research communities collaborate and cross-pollinate ideas. In the downtown core, gleaming skyscrapers of machine learning house neural networks that process information in ways that mirror human brain function. The historic district preserves the elegant, rule-based approaches of symbolic reasoning and formal logic, the classical architecture of AI's foundational years. Specialized suburbs spread throughout this intellectual landscape, computer vision experts teaching machines to perceive and interpret visual information, natural language processing researchers enabling computers to understand and generate human language, and robotics engineers bringing intelligence into physical embodiments. What makes this metropolis truly dynamic is the constant interaction between these neighborhoods, where breakthroughs in one area immediately ripple through the entire infrastructure, transforming approaches across all domains of artificial intelligence research. Our first major research theme focuses on multi-agent systems and coordination. Imagine conducting a symphony orchestra where every musician is an artificial intelligence agent, each possessing unique capabilities, timing, and understanding of the musical score. 4 papers in today's collection address this fundamental challenge of enabling multiple AI systems to work together effectively without interference or conflict. Yang and colleagues present AIS agents, a unified framework utilizing what they term multipolar task processing graphs, sophisticated choreography charts that enable agents to coordinate their actions dynamically and adapt to changing conditions. Meanwhile, Tomasev's research team ventures into even more ambitious territory, exploring virtual agent economies where AI systems might engage in buying, selling, and trading resources with each other at scales and speeds that would make human markets appear leisurely by comparison. These advances point toward AI ecosystems, where individual agents contribute to emergent collective intelligence. The second dominant theme centers on robustness and reliability, the engineering equivalent of constructing bridges capable of withstanding unexpected storms and unprecedented loads. As AI systems become increasingly prevalent in critical applications, ranging from medical devices to autonomous vehicles, their reliability transforms from a technical preference to a literal matter of life and death. Reid and colleagues investigate how information theoretic measures can function as sophisticated early warning systems for AI failures, essentially creating diagnostic tools that detect when an AI system is approaching a mistake before that mistake actually occurs. Shazman's research team develops robust planning algorithms specifically designed to handle uncertainty and incomplete information. Imagine AI systems that maintain optimal decision-making capabilities even when operating with partial knowledge about their environment or facing unexpected situations that weren't included in their training data. Our third major theme explores explainability and interpretability, addressing the fundamental challenge of building AI systems capable of articulating their reasoning processes. Consider the frustration of working with a brilliant colleague who consistently provides correct answers, but can never explain their thought process or reasoning methodology. Multiple papers tackle this transparency challenge from different perspectives and application domains. Armody Friedman and colleagues systematically evaluate various approaches to making AI decision-making processes transparent, particularly focusing on systems that make binary yes or no determinations. Jullien's research team introduces compartmentalized agentic reasoning specifically for clinical applications, creating medical AI systems that not only generate diagnostic recommendations, but can walk healthcare professionals through their reasoning step by step, much like having a physician who explains every piece of evidence considered and how that evidence contributed to their final diagnosis and treatment recommendations. Among the wealth of discoveries presented in these papers, 5 findings emerge as genuinely revolutionary, each possessing the potential to fundamentally reshape how we construct and deploy artificial intelligence systems in real-world applications. The first breakthrough emerges from Reid and colleagues' investigation of learning dynamics, where they discovered that successful AI learning produces distinct information signatures that can be measured and tracked throughout the learning process. West's team developed the abduct-act-predict scaffolding framework, transforming failure analysis from educated guesswork into structured detective work, with remarkable accuracy improvements. O'Doherty's comprehensive study reveals strikingly consistent moral biases across 6 different AI models, raising profound questions about embedded ethical frameworks. Jullien's medical AI system achieves extraordinary diagnostic accuracy while providing complete explanations of its reasoning process. Finally, Shazman's work introduces the first online planning algorithm for robust decision-making that comes with mathematical guarantees about performance quality, even under conditions of uncertainty and incomplete information. Today's featured paper represents Reid and colleagues' groundbreaking work on mutual information tracks policy coherence in reinforcement learning, a study that fundamentally transforms our understanding of AI learning dynamics and system monitoring capabilities. This research addresses a deceptively simple yet profound question. When an AI system learns through trial and error, what actually occurs within its decision-making processes? For decades, reinforcement learning has operated as something of a black box, where researchers could measure performance improvements, but the internal mechanics of learning remained largely mysterious. Reid's team approached this challenge using the mathematical tools of information theory, the same framework underlying data, compression, and communication systems. They systematically tracked how information flows through AI systems during learning, measuring mutual information between observations and actions, entropy measures, capturing behavioral uncertainty, and joint relationships between states, actions, and outcomes. Their methodology included studying both successful learning and systematically introduced failures to create diagnostic signatures for different types of system malfunctions. Reid's team discovered that successful AI learning produces a distinctive information signature characterized by mutual information between observations and actions, steadily increasing from 0.84 to 2.83 bits, representing a remarkable 238% growth during training. This mathematical progression reflects the development of what we might call situational awareness, as the AI learns to make increasingly informed decisions based on environmental observations. Even more fascinating was their discovery of an inverted U-curve pattern in joint mutual information, where early learning phases show increasing values as the AI explores strategies and understands cause and effect relationships, followed by decreasing values as the system becomes more specialized and efficient. This pattern mirrors human expertise development, where initial learning involves broad exploration of possibilities, eventually focusing on the most relevant and effective approaches. Their research also revealed that different failure types produce distinct information signatures. Sensor faults create broad collapses across all information channels, while actuator faults selectively disrupt outcome prediction while preserving situational understanding. The real-world implications of Reid's information theoretic monitoring framework extend far beyond academic curiosity into practical AI safety and reliability applications. This research provides a universal approach for understanding and monitoring AI systems that functions regardless of specific architecture or application domain, whether dealing with robotic systems, learning motor control, AI managing power grid operations, or autonomous vehicles navigating complex urban environments. The framework enables early detection of system degradation before catastrophic failures occur, supporting the development of adaptive AI systems capable of autonomous fault detection and self-correction. In critical applications such as medical devices, financial systems, and transportation networks, the ability to detect and diagnose failures before they become catastrophic represents an essential advancement in AI safety. This work establishes foundations for AI systems that can recognize when they're confused, request human assistance, or gracefully degrade performance to maintain safety standards, while alerting operators to potential issues requiring attention. Looking toward the future, these 15 papers collectively point toward exciting developments in AI research that feel less like science fiction and more like inevitable destinations on our current technological trajectory. AI development is evolving from individual standalone systems toward interconnected ecosystems, reminiscent of mature forest environments, where different AI systems interact, support each other, and create emergent behaviors that no individual system could achieve independently. The multi-agent research suggests AI systems that will coordinate seamlessly across different domains and scales, with AI assistants collaborating not just with humans, but with other AI systems, sharing information, dividing tasks, and combining capabilities in real-time optimization. We're witnessing early foundations of virtual AI economies, where artificial agents might trade computational resources, data, and services in ways that optimize outcomes for entire networks of interconnected systems. Advances in explainable AI point toward truly collaborative rather than merely assistive artificial intelligence, where systems can articulate their reasoning processes and engage in meaningful dialogue about decision-making approaches. Today's exploration of cutting-edge AI research reveals a field rapidly maturing from proof-of-concept demonstrations toward systems with real-world reliability guarantees, built-in explainability features, and sophisticated self-monitoring capabilities. The critical advances we've examined in coordination mechanisms, transparency frameworks, and safety protocols represent essential building blocks for trustworthy AI deployment in high-stakes applications. However, these discoveries also illuminate new challenges, particularly regarding the values and biases that AI systems inherit and propagate throughout their decision-making processes. The revelation of consistent moral biases across different AI models demands urgent attention and systematic solutions to ensure these systems align with diverse human values and ethical frameworks. Information theory emerges as a powerful new tool for AI monitoring and diagnostics, providing mathematical foundations for understanding system health and performance. As we advance toward more sophisticated AI capabilities, the research community must balance innovation with responsibility, ensuring that tomorrow's AI systems serve humanity's best interests while maintaining transparency, reliability, and ethical alignment. This comprehensive analysis was created through AI synthesis using Claude Sonnet 4, released on May 14, 2025, with text-to-speech synthesis powered by advanced Deepgram technology and image generation through OpenAI systems. The content underwent human expert review to ensure accuracy and clarity of the synthesized research summaries. While every effort has been made to accurately represent the original research findings, some oversights may exist, and listeners are encouraged to consult the original papers and references for complete technical details and nuanced arguments. The synthesis process demonstrates the current capabilities of AI systems in processing, analyzing, and presenting complex technical information, while highlighting the continued importance of human oversight in ensuring accuracy and appropriate interpretation of scientific research. This collaborative approach between artificial intelligence and human expertise represents the kind of productive partnership that these research papers suggest will become increasingly common in academic and professional contexts. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates on cutting-edge AI research and breakthrough discoveries that are shaping our technological future. Join our community of forward-thinking professionals and stay connected with the innovations that will define tomorrow's intelligent systems. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org, content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.